So it's a pleasure for us to have Giacomo, unfortunately only online, but it's a pleasure to have him tell us the first part of a story that will be continued tomorrow by Bianca. So he'll present part one of talk about the variational model for two-dimensional ferronematics. So please.
Well, thank you very much. Thank you, Agir, and I'm grateful to the organizers and to the Isaac Newton Institute for giving me the opportunity to participate in this workshop, even if only remotely. I deeply apologize to the organizers, the Institute, and all of you for not being able to make it physically in person, but I'm still very grateful that I have this chance. And I'd like to take this chance to talk about some joint work with Apala Majumdar and Bianca Strofolini, who are both in the audience, and why we won. And as Argir just said, this is the first part of a two-part talk. So tomorrow, Bianca Strofolini will tell you about the sequel of the story, and that's some joint work in collaboration with Federico Di Pasquale as well. So what is the topic of the story? This is about ferronematics, and this is why it fits within the context of this workshop, so the mathematical design of new materials, because as far as I understand it, ferronematics are composite materials which have been theorized since quite some time. They were theorized proposed theoretically in the 70s by Brochard and degli, but they have been realized experimentally much later than that in recent years. And what are they? They are composite materials which are composed by magnetic inclusions, magnetic particles embedded in a host, in a nematic liquid crystal host. And well, the magnetic inclusions typically are much larger than the molecular length scale of the nematic liquid crystals, but still there is some sort of interaction that goes on close to the boundary of the particles of the magnetic inclusions, and as a result, the effective properties of the composite material, they are different as compared to the original properties of the nematic liquid crystal host. So they were proposed by Brochard and degli precisely because of that, precisely because ferronematics have a much higher magnetic response as compared to nematic liquid crystals alone. And today I will be talking about a mathematical model for such objects. As you can probably, I suppose some of you in the audience already know me, but those of you who will not know me, they probably guessed based on my very low-tech approach to imaging that I am a mathematician. So if you have questions on the physical side of the model, I'll try to answer my best, but I'm afraid I'm not specialist in this. So what's precisely the topic of my talk? Again, mathematical model for such objects, for ferronematics in 2D. It's a two-dimensional work only, which is based on two papers. This is why the two parts of the talk. Today we're going to look, it's a variational problem, so it's formulated in the language of the calculus of variations. There's a free energy functional to minimize. And today we are looking at minimizers of the free energy functional. Tomorrow, Bianca Strofolini will tell you about non-minimizing critical points of the free energy functional as well. So where does the model come from? It's not our model. We lifted from papers by Bisht and co-authors. And itself, I believe the model was inspired by experiments by Mertesi and collaborators. The model is consistent with other models that have been proposed following some homogenization approach. For instance, there's a paper by Carme Calderen, De Simone, and Golovati and Panchenko, who studied a homogenization problem precisely to describe ferronematics. And as a consequence of their work, they rigorously justified, they derived by a rigorous homogenization result, an homogenized model for ferronematics. It's not quite the model that I'm going to tell you about today, but there are some similarities, particularly in the coupling part of the model. And as long as the homogenization approach for a pneumatic liquid crystal goes on, there's other work in that area, particularly by Zarnescu and co-authors. There's a recent paper by Dean, National-Mekempeng, and Zarnescu. They're studying homogenization for pneumatic liquid crystals in fluid mechanics context as well. But today I'm not going to focus on homogenization. I'd like to take the model for ferronematics as a given and move on from there. So how do we model ferronematics? Well, first of all, this is a two-dimensional model. So we consider a domain omega in R2 that's a bounded and smooth, or say Lipschitz, simply connected domain. I apologize for the typo in there. This is the physical container for our ferronematics. And since ferronematics are composite materials with essentially two components, we have two order parameters to describe them. So there will be an order parameter for the liquid crystal component, and that's a Landau-Dejean Q tensor. It's a 2x2 matrix field. That's real matrices. It's a field of symmetric and trace-free matrices. And we had already reminders during this workshop of Q tensors, so I will not spend a long time on them. However, I do stress that this is a two-dimensional model, and we assume that the molecules are, constrained to lie in planes. So this is really a 2x2 matrix field that we are using. It's fully two-dimensional Landau-Dejean theory for the pneumatic liquid crystal component. And as for the magnetic inclusions, what we use is a vector field. That's the magnetization vector for the magnetic inclusions. Now, so far, my vector field is just a vector without any constraint or restrictions. There is no saturation constraint imposed in the model so far, but as you will see, it's going to come up in a second through the free energy functional. So there is indeed some sort of saturation constraint embedded in the models. It comes through the free energy function. And this is the free energy functional which we are working with. It's written here in non-dimensional form. So everything has been rescaled away and it has been simplified and written in non-dimensional units, non-dimensional form. There are mainly three components to this free energy functional. One component for the liquid crystal part, and this is what you see in blue. There is one component for the magnetic inclusions, and it's what you see in red. And there's a coupling term between the magnetic inclusions and the liquid crystal host. It's what you see in green here. So as long as the liquid crystal is concerned, we are looking at some Landau-Dejean free energy with a one constant approximation. And for the potential, we are working with a two-dimensional setting. So the trace of Q cube is equal to 0 in this restricted two-dimensional setting, and therefore up to some additive constant, you can write down the standard quartic Landau-Dejean potential in this particular form. Now, for the magnetic component, we have essentially a Ginzburg-Landau energy. There is a potential part in here for the magnetic component. This is where the saturation constraint for the magnetization vector is imposed. And there is an additional gradient contribution for the magnetic vector. It's some sort of term with some regularizing effect in the free energy, if you will. And then there is something very important in the model, which is this magneto-pneumatic coupling term in here, Qm.m. It's consistent with the symmetry of the problem. It's also consistent with the homogenization approach by Calderer and collaborators. And it has several different effects depending on the parameter that you take in front of it. So here we have negative C0 in front of the coupling term. In this talk, we are focusing on the case C0 is positive, so overall a negative sign in front of the coupling term. And this has the effect of favoring configurations where the magnetization is parallel to the pneumatic director. If you were to take C0 negative, to be negative, then the preferred configuration would have the magnetization orthogonal to the pneumatic director. So depending on the sign of C naught, you can play around a little bit with that. Also, I forgot to say something very important. This model is only valid when the temperature is low enough, so it's below the isotropic nematic transition point, but not too far below, otherwise you are out of the applicability range for the Landau-de Gennes theory. So if you wanted to consider higher temperatures, then you would have to consider a different free energy, and in particular, the potential part for the Q component would have to be slightly different. This is specific to this particular regime of temperature. And in addition to that, you can see you have at least three parameters in the free energy functional. They are non-dimensional parameters. They're psi, which is in front of the magnetic component of the energy. There's an epsilon in here, which is in front of the potential part of the energy. And again, there's the C naught in front of the coupling term. Of course, you could consider plenty of regimes, but today in my talk and in Bianca's talk, I suppose we are focusing on a very, very specific regime of parameters, which is the following. Epsilon, psi, and C naught are all positive, and they are all small, and they are comparable to one another. They are of the same order. In fact, to simplify things, we will take psi to be exactly equal to epsilon. You could vary a little bit, but I suppose it wouldn't affect qualitatively the results too much. Just the constants would be more complicated to track. And we take C naught to be proportional to epsilon. C naught is equal to beta times epsilon. Beta is positive and fixed. So epsilon is small, and it will go to 0, in fact, in a second, but beta is positive and fixed. It's of order 1. You could consider different regimes. We have played a little bit around, but we chose to focus on this one because there's something interesting going on, and I'll try to elaborate on that in a few slides. Now, before I move on, well, first of all, this is the form of the free energy functional once you plug in the assumptions on the parameters we've just made. So everything now is written in terms of epsilon, and there is an additional parameter beta in front of the coupling term, which is now fixed. But we are interested in the limit as epsilon tends to 0. So we are looking at minimizers of this functional, and we will study it subject to some appropriate boundary conditions, and we will study the limit as epsilon tends to 0. Now, just as a reminder, minimizers of the functional, of course, satisfy a system of PDEs, the Euler-Lagrange equations, which are recalled in here. They're not going to be that important in my talk because I'm looking at minimizers, so we can exploit the variational structure of the problem, but they will be very important in Bianca's talk tomorrow because she will talk about general solutions to this set of equations, whether or not they are minimizing the functional. So I'm not going to comment a lot on the equations, just they're there in the background. But I will comment on the boundary conditions because we minimize subject to fixed prescribed boundary conditions. And for simplicity today, I'm considering Dirichlet boundary conditions for both Q and M. So more precisely for the Q component, the liquid crystal component, I suppose the boundary datum is orientable. So everything is written in terms of a unit vector field defined on the boundary, NB in here. This is a unit vector field which is smooth enough, it's regular. That means Q is orientable at the boundary. And there is a very prescribed and constant order, the scalar order parameter in front of this vector field, of this tensor field, if you want, in here, that's chosen in such a way as to minimize the potential part of the energy up to negligible terms. And there is a Dirichlet boundary condition for the magnetization vector as well. And as you can see, the direction of the magnetization of the boundary is the same as the direction of the, the director of the liquid crystal component. So the eigenvector for Q on the boundary corresponding to the positive eigenvalue. And there is again a constant parameter in front of the NB in the boundary condition for the magnetization. And again, this constant parameters are chosen in such a way as to minimize essentially the potential part of the free energy functional. So as a consequence, because we have chosen orientable boundary conditions for both Q and M, the boundary datum will carry a topological degree, and the topological degree is an integer. I will denote it by D. Now, I'm not an expert again, but as far as I understand, taking Dirichlet boundary condition for the magnetization vector is something not quite standard. Sometimes people prefer to consider Neumann boundary conditions for the magnetization vector. Now, if you want to take Neumann boundary condition for the magnetization, then you can do that. And we have results that cover this case as well. Perhaps Bianca will tell you about them tomorrow or not, I'm not sure, but we did study the Neumann boundary condition case as well. There are some differences in the statement, some modification that have to be made. And so just to simplify the statement today, I'm focusing on the case of Dirichlet boundary conditions. But just know that if you prefer Neumann boundary conditions, it's fine, you can do them as well. For the magnetization, we always keep Dirichlet boundary conditions for Q, though. Now, this is the setup of my problem. So what happens? I have a functional, I have boundary conditions. There will be minimizers for any fixed positive value of epsilon. That's easy to prove by the direct method of the calculus operations. What happens as epsilon tends to 0? But here is some heuristics. If we only look at the Q component of the energy, well, when epsilon is small, we do know that there will be defects, topological defects that occur, and they will have a certain type. For instance, suppose that our domain is a disk in 2D, and suppose the boundary condition is radially symmetric, so something of Hadjab type. Now, of course, you could consider a Hadjab type configuration that satisfies the boundary condition is what you have on the left, and this configuration has a topological defect with degree equal to 1 in the center. But when epsilon is small enough, we know that it's actually favorable to split something like this, which is similar to what we saw in Radu's talk just before. It's preferable to split it into 2 defects of degree 1/2 each, because the energy of a defect is proportional to the square of the degree, and so 2 defects of degree 1/2, they cost less energy as compared to 1 defect of degree 1. So this is from the point of view of the liquid crystal alone, and there is no problem with non-orientable defect, of course, from the point of view of the liquid crystal. But now there's not only the liquid crystal in our system, we have the magnetization as well. And the magnetization by nature is a vector field, so it is an oriented quantity. It does carry an orientation as well as a direction. So if you look at a configuration on the left, well, you know that the magnetization in this particular choice of parameters tends to stay aligned to the nematic directors, and it's perfectly fine because the configuration on the left is orientable. But if you look at the configuration on the right, then you see a problem because you have non-orientable defects in the Q component. And then if you try to orient them by using the magnetization, then necessarily you will be forced to have a jump in the magnetization profile to accommodate for the presence of non-orientable point defects in Q. So several configurations can happen. What turns out in that in this particular regime of parameters, at least, the configurations that's energetically preferred is still the one on the right, which has both points and line singularities for Q and M respectively. And I suppose you can guess it, you can guess it from the point of view of mathematics because of the scaling already. Just the scaling of the M component of the energy, there's an epsilon in front of the gradient term and 1/epsilon in front of the potential term for M. So it's immediately reminiscent of the modica mortale phenomenon. And this is confirmed by numerics as well. This is a gradient flow simulation, which was performed by Wei Wang. The slide is divided into two halves vertically. So there's two columns for each set of simulations. The first column here is for the Q component with a given value of epsilon, and it's a gradient flow simulation. So from the top to the bottom, time is increasing. And then the second column is the corresponding M configuration. While if you go on the right-hand side of the slide, you have something similar, except it's a different set of parameters. So let us focus on the left-hand side of the picture first. The color scale represents the absolute value, both of Q and M. So the blue regions corresponds to regions where Q is very close to 0 or M is very close to 0. They are defects. And as you can see, in this particular set of simulations, we started from an initial condition that was of a Hedgehog type. It had one defects of degree equal to 1. It's not shown here in the picture, but very soon the initial defect split it into two separate defects for Q, and they are non-orientable defects of degree 1/2 each. And then as time moves on, these defects tend to move apart from one another. And correspondingly, there's a line defect for the M component that originates, and it sort of joins the the defects for the Q component. This is what you can see in the simulation as time progresses. And here on the right-hand side of the slide, you have a similar phenomenon, except you have taken we have taken a smaller value of the parameter epsilon, and this is why the regions, the blue regions, they are smaller because they are proportional. Their size is proportional to the parameter epsilon. This is something similar, except that we started from an initial condition with degree equal to 2, and so it's split into 4 defects, each of degree equal to 1/2 for the Q component. And they are joined by line defects for the M component, and as time progresses, the line defects for the M component tends to get closer and closer to strain line segments. So this is the heuristic, and in the rest of my talk, I'll try to make this heuristic rigorous by stating and perhaps just giving a hint of the proof of a theorem. So it's a rigorous convergence theorem for minimizers as epsilon tends to 0. Now, before I can state the theorem, I need to recall some preliminary notation. And the first item of notation is just something very classical, which originates in the Ginzburg-Landau theory. If you look at the energy for the Q component, that's really a Ginzburg-Landau energy, in fact, because they're working in 2D. And as we all know, there's a very, very extensive literature on the Ginzburg-Landau functional. There's in particular this monograph where it all started from. It has been quoted already in Rado's talk and in other talks, I'm sure, by Bétuel, Brésis, and Hélin. So this is some notation they introduced, which I just recall here. Let's say we're given some finite number, an even number of points, distinct points in my domain omega. I will define the canonical harmonic map associated with these points and my given boundary condition. It's going to be a map from the given domain to a distinct set of matrices. It's the Q tensor with unit norm. So my canonical harmonic map is going to have unit norm everywhere in the domain, or almost everywhere in the domain. It's going to be smooth away from the designated points in my domain omega. And the prescribed points, it's going to have non-orientable singularities, and the singularities are going to have degree equal to either 1/2 or minus 1/2, depending on the sign of the boundary degree. And finally, it's called the canonical harmonic map because it satisfies a certain PDE, a certain nonlinear PDE that is to be satisfied in the sense of distribution everywhere in the domain. But as it turns out, when you look into it more closely and you stay away from the singularity, that PDE reduces to essentially a nonlinear way of phrasing Laplace's equation for this maps with values in this unit circle of matrices. So it's just Laplace's equation essentially away from the singularities. And once you prescribe the boundary condition and the singularities, well, the canonical harmonic map is unique. So now, given the unique canonical harmonic map, you can remove some disks of radius sigma around the singular points. You can compute the Dirichlet energy, the gradient energy of this particular map. You can subtract away the leading order term of the energy, which is proportional to the logarithm of sigma, and you take the limit as sigma tends to 0. This is a so-called renormalized energy, which has been introduced again by Bituel, Bresis, and Hélin. It's some sort of interaction energy between the points singularity. And in my talk, I think of it as being some sort of Coulomb-like repulsion interaction between the point singularity. Of course, it's not exactly Coulomb-like repulsion between the singularities. It's much more complex than that. But I think of it as being some sort of overall repulsive term, because as the singular points approach one another, the renormalized energy blows up. So the renormalized energy wants the singular points to be apart from one another. Overall, I think of it as being repulsive in my talk. Now, this is something classical. I need to introduce another set of notation, which is also classical, but with a slight twist. And it goes as follows. Again, suppose we are given an even number of distinct points in omega. I will define, of course, it's an even number of points, so I can take any 2 points and I can join them with a straight line segment. And then I can take other 2 points, any 2 points, and I can join them with another straight line segment. And since I have a finite even number of points overall in my domain, I can join them by an even number of, by some integer number of straight line segments overall. Now, of course, this can be made in several different ways, in finitely many different ways, though. And I can look at the total length of my straight line segments, and I can now minimize the total length of the straight line segments over all possible ways of combining my points. And this is what I call the length of a minimal connection for the given points A1 to A2 modulus of D. So this is what I denote by bold L, and I will say that a certain set of straight line segment is a minimal connection for these points when it's a minimizer for this geometric variational problem. Now, I think of this length of a minimal connection, this bold N, as being some sort of geometric energy, so to speak, associated with the points. And if you allow me this way of thinking, this is some sort of attractive interaction between the points, because of course, the way of minimizing L would be to have all the points coinciding with one another, so you'd need no segment at all to join them, and this bold L would be 0. So this is some sort of attraction between the points. Now, if you're familiar with the harmonic maps literature, this is already a variant of something that has been introduced and studied in that context. In a paper, very famous paper by Bresis, Coron, and Lieb, they introduced the notion of minimal connection associated with harmonic maps, and that was studied again by Almgren, Browder, and Lieb, generalized greatly, and has a rich story going on. There's a slight difference between the minimal connection in the sense of Bresis, Coron, and Lieb and the one we consider here, because if you know about that paper by Bresis, Coron, and Lieb, they had distinct sources and distinct sinks in their problem. So a straight line segment in Bresis, Coron, and Lieb was only allowed to go from a designated source to a designated target. Some points were marked -1 and other ones were marked +1. But here we do not have this restriction. You can take line segments between any point you like and any other point you like in your domain, and there's no difference whatsoever between sinks and sources. Everybody's the same. So in technical jargon, the minimal connection in the sense of Bresis, Coron, and Lieb is a solution of a plateau problem with multiplicity in the integers, while here we're looking at a plateau problem with multiplicity mod 2. And this is all the difference. This is because we're looking at non-orientable defects, of course. And now, having introduced my notation, I can state the main result of my talk. Let's say we have a sequence of minimizers. Q epsilon star, M epsilon star is a minimizer of F epsilon subject to the boundary conditions that I described to you earlier on. Now, as epsilon goes to 0, there is a non-relable sequence that satisfies the following properties, the following conditions. So first of all, there's compactness for the Q epsilon star component. So the Q component, the liquid crystal component converges, and the limit for the Q component is a canonical harmonic map with singularities at some even number of points. They're going to be non-orientable singularities of degree -1/2 or +1/2, depending on the sign of the boundary degree. Now we have compactness for the M component as well. And the limit for the M component is going to be a lifting, if you will, for the limit of the Q component. So the M star is going to be a vector field with constant norm, and the constant is a certain constant that minimizes the potential part in the energy. And moreover, the M star is precisely equal or proportional to the molecular director. It's an eigenvector of Q star associated with a positive eigenvalue. However, the M star belongs to this funny space. It's SBV. If you haven't seen the space, it means, it means that the M star is not necessarily going to be smooth. The M star is going to be discontinuous, possibly. In fact, it will be discontinuous necessarily. It has jump discontinuities. And we can say something a bit more precise about the jump discontinuities of M star in the case the domain is convex. So assuming that the domain is convex, then we know for a fact that the jump set of M star will be a finite union of straight line segments. And in fact, it's not just any straight line segments, it will be a minimal connection associated with the topological defects, the non-orientable defects of the Q star component. So really the picture is the Q star, the Q component, the liquid crystal has non-orientable defects of degree minus or +1/2, and M star, the magnetization vector, has line singularities that connect these defects in pairs along straight lines, and they do that in such a way as to minimize the total length. And moreover, we can say something about the optimal location of the singular points for the Q star component, because they will be such as to minimize a certain total interaction energy. And the total interaction energy has two contributions. There's a Ginzburg-Landau contribution, which is the classical renormalized energy à l'habituelle Brésil-Célin that I have introduced already in my talk. But there is an additional contribution weighted by a parameter that depends on beta. And this additional contribution is nothing but the minimal connection, the length of the minimal connection associated with the singular points. So overall, there is a combination of effects. There's a overall repulsive interaction, which is mediated by the renormalized energy. And there is some attraction, some additional attraction, which is the length of a minimal connection. And I suppose it makes sense because well, if you have this M component as well, and you need to pay some sort of energy in order to create line defects for M, then you'd want the defects to be a bit closer to one another, because that saves you something in terms of the M energy. Now, just as a side remark, there was a slightly different context. In fact, from the point of view of the mathematics, a considerably different context where a similar renormalized energy that consisted of two contributions appeared. In particular, there's a paper by Rufat Badal, Marco Cicalese, Lucia De Luca, and Marcello Ponsiglione. It was again a paper for a mathematical model for nematic liquid crystal. However, they were considering a discrete problem. What's interesting is that in a different setting, with a different setup that I'm not going to describe here because of time, even though it was very interesting, they were able to recover, in fact, essentially the same renormalized energy that you see in here, with this term that's the Ginzburg-Landau BBH renormalized energy, and another term which, I mean, they did not quite write, they didn't quite write it as the length of a minimal connection, but it's equivalent to the length of the minimal connection. So the same interaction energy occurred as a limit from a different problem, a discrete one, which I found interesting. And if I have perhaps 5 minutes or so, perhaps I can give you just a quick hint about the proof of this theorem before finishing up. Now, how did we go around proving the convergence theorem? Well, we divided and conquered, hopefully conquered, but we divided. We divided the Q component in a way, and then we divided again in another sense when it came to the M component. For the Q component, that's in a way the dominant contribution to the energy, well, then you can use arguments and you can use existing results from the Ginzburg-Landau theory, because effectively the Q terms in the energy, they are the Ginzburg-Landau energy. So you can prove compactness by appealing to that technique, by appealing to that literature, by appealing to these techniques. Now, once you identify the position of the defect points, and you can do that in some way by existence result in the Ginzburg-Landau literature, then you know for a fact that so long as you stay away from this position of the singularity in the limit, the Q tensor will be bounded away from zero. It will have non-zero scalar order parameter. It will have a non-zero norm, and therefore it will have well-defined eigenvalues and eigenvectors. So instead of working with the original variables, we use a change of variables. Instead of having the magnetization vector expressed in terms of the canonical basis of R2, we consider a magnetization vector expressed in terms of the orthonormal frame of eigenvectors for Q. So effectively, we define another vector field, U epsilon star, whose components are given as follows by taking scalar products of M against the eigenvectors of Q. And if you do that, there's a nice thing that's some sort of decoupling in the free energy function. If you do that, the Q component will decouple for the U component. So for the Q component, you will have a Ginzburg-Landau looking free energy. The potential part in here is not exactly the same as what you had before. There's some additional contribution that's coming from the coupling curve. But still, this is a functional of Q only. And then you have a functional of U only, with some sort of effective potential, so to speak, H. This is a double well potential for the U component. And there are some additional terms which are still coupled between Q and U, but they are negligible. They are going to zero as epsilon tends to zero. So effectively, you've decoupled your free energy functional, and now you can apply techniques from the vectorial modicum orthogonal problem. And as a side remark, there was a topological lower bound as well that was used in the proof. I suppose it's sort of, I mean, it makes sense when you think about it, but we weren't able to find it written exactly the way we needed it in the literature. Perhaps you will be able to provide me with references, but say we reproved it. If you have a Q tensor with a finite number of a finite and even number of non-orientable singularities, and if you have a lifting for Q, so sorry? There's okay, I'm sorry. I'm sorry, there was something going on. I didn't quite understand, but I'm also, I'm close to finishing, very close to finish it, perhaps a couple of minutes or so, even less. If you have a lifting for Q, so a vector field in SPV with constant positive norm, which is proportional to the director for the corresponding Q tensor, then the jump set of M, which I denote here by the letter S of M, it's going to satisfy a lower bound for the length. and that is the length of the jump set for M on your convex domain is going to be greater than or equal to the length of the minimal connection. I suppose it sort of makes sense when you think of it, because topologically, the jump set of M needs to join defects, needs to join the non-orientable point defects of Q, and the boundary of the jump set needs to be equal to the non-orientable point defects. So if you want to join them, I suppose the shorter way you can do that is to go by straight line segments, and then the shortest way of doing that is to just consider a minimal connection. So the length of the jump set cannot be less than the length of a minimal connection. This is, I suppose, fairly easy to understand. It was a little bit less easy to prove, because when you have an SBV vector field, the only thing you can say for sure on the jump set of it is that it will be rectifiable, and rectifiable set, well, that's a very, very low notion of regularity, and in particular, rectifiable sets do not carry a notion of a boundary. So saying that the boundary of the jump set needs to be the non-orientable singularity makes sense intuitively, but rigorously, it's a bit delicate to work with. So this is it, I suppose. The conclusion of my talk will be that we have a simplified model for ferronematics in 2D, which couples this Q tensor which is non-orientable with some oriented quantity. And in this particular regime of parameters, we see both points and line defects in these two different components. There's still plenty of things to do. And the first thing would be to extend from minimizers to non-minimizing solutions, but this is precisely what Bianca will pick up tomorrow. So I leave you in very, very capable hands. And I thank you all very much for your patience. Once again, sorry for not being able to be there physically. Thank you.
Thank you, Giacomo. Questions, comments? Yeah.
Hi, Giacomo, thank you. I have a question about the boundary condition. I understand why you would want to impose the boundary condition for Q, but can you explain why you want the boundary condition for M to be particularly that? I mean, maybe practically it would be difficult to arrange that, or why would you do that? Why wouldn't you want to impose, say, a constant magnetization field, say?
Right. Well, thank you very much for your question, Luke. And well, again, the Dirichlet boundary conditions, we started with them because they were mathematically simpler to deal with, and they still showed a lot of the phenomenology that you see with other type of boundary conditions that we consider. So Neumann boundary conditions for the magnetization. I suppose as far as the interpretation goes, Neumann boundary conditions are sort of more widely accepted. And again, if you wanted to do that, there's no problem whatsoever. For the Dirichlet boundary conditions, once we decided to go with the Dirichlet boundary conditions for both Q and M, then this particular choice for the boundary conditions sort of made sense to us, at least, mathematically, from a purely mathematical point of view, because in this way, when you look at the potential part of the energy, which is in here, well, the potential part of the energy is going to be, let's say, not exactly equal to zero, because it turns out that the minimizers for this potential part of the energy, the set of minimizers depends on epsilon as well. And so if I want to minimize this potential energy for a given value of epsilon, I obtain a certain set of minimizers. If I want to minimize for a different value of epsilon, I obtain a slightly different set of minimizer, and so on and so forth. But in the limit as epsilon goes to zero, the set of minimizers for my potential energy converges precisely to something of this form. So overall, it's the same sort of rationale that I suppose people typically impose in the Landau-Dejean theory when you impose Dirichlet boundary conditions for the Q component alone with a prescribed value of the scalar order parameter, and that given value of the order parameter is chosen in such a way as to minimize the potential part of the energy. And here we do something similar. It's the same rationale, except we do it for both Q and M. But this is it. Whether it will be convenient to impose it physically, I mean, I suppose that for the Dirichlet boundary condition, it's something, as long as you take something, say, homeotropic or planar, it's some sort of acceptable approximation. For the magnetization vector, I am less sure. Perhaps Neumann would be another choice that's interesting from that point of view. But again, from the mathematical point of view, the rationale was just minimization of the potential part. I hope it answered the question.
Thanks.
Thank you.
Yes.
Hello. So I might have maybe missed something, but I was wondering about this idea that all the defects have repulsive interaction between each other. And my question is, how general is that? How general is the model for a system which have defects of opposite ecological charges as well?
Well, thank you very much for this question. Once again, I am not an expert on the physics, so when it comes to the physical modeling, I can only provide something that is based on my intuition of the mathematical side. But on the mathematical side, so long this technology to construct this renormalized energy, essentially it worked because, it worked because you have an order parameter that's confined or close to the unit circle. So for the Q, the Landau-Desjardins Q tensor, in this particular regime of parameter, in particular when you take this asymptotic limit, the Q tensor will want to have a scalar order parameter that's fixed. And because it's 2D, that means that essentially the limit Q order parameter, it lives in a unit circle. You can vary the director, and you can vary it in 2D, so you have a Frenon on the unit circle, but you cannot vary so much in terms of the order parameter because it's prescribed by temperature and so on. And in this particular regime of parameter, that's a fairly rigid restriction. Now, so long as you have some sort of system which is described by this circle-like structure, then the mathematical analysis should carry over, at least physically speaking, of course. For the simpler cases, perhaps one constant approximation and so on, going beyond the one constant approximation is much more delicate, but I suppose things are a bit moving now. Anyway, the short answer is, so long as you have a system that is described by a circle symmetry, I think you can do something in the ways of writing down this renormalized energy, as it's called. When you move on to systems that are described by other spaces for the order parameters, perhaps other manifolds, that becomes a lot more complicated. There are progress on the mathematical side, very recent one, but it's more delicate and much less explicit. So you can wiggle around a little bit, but maybe a bit less. I hope it answered the questions. I'm not so sure it did.
Yes, thank you.
Thank you very much for the question.
Well, thank you very much. That was a beautiful talk. So I have a question or a double question. Let's see. So you're taking beta positive, right? Which is the coefficient of the say magnetization coupling there. Oh, here you call it. No. What is that? I lost it now.
C0.
That's C0. So hold on. Right.
Oh, sorry. Here
okay, that's you changed name. Yeah. Right. So and this corresponds, say, to a needle system, right? So with basically the prototype by Desjardins and Bronsard. Brochard, I should say.
Yes.
So what would happen if you take beta negative, which that would cover the case of platelets, right? So, and for what I see, so okay, my general question would be if this is significantly different, especially in terms of the effects, and in particular, what this does to the normalized energy, because could actually look at the attractive interaction in that energy, right? Because I think when beta is something like -0.5, you just look at that term with the lines interact. So so in other words, do the case of B negative would be significantly harder, and of course, would you expect very different outcomes?
Well, thank you very much. This is a great question, and it goes into the broader question of moving around with in the parameter space. We focus on a very special regimes, but there's plenty of other ones, right? So to your point, more to the point, I suppose that at least from the mathematical point of view, when you are still in this purely two-dimensional setting and you take beta to be negative, I think it shouldn't vary too much, because after all, in 2D, there's not a lot of room. If you perhaps replace M by the orthogonal of M, it doesn't change the gradient energy, it doesn't change the potential, and it would essentially change the sign in here. But that's an artifact of being in 2D, and in 2D you have a lot less room to move around, right? If we were to go in a fully three-dimensional system, then first of all, everything would be much more delicate than I just, obviously, than I just told you now, and we didn't look into it in depth. And I'm positive that in 3D, there will be much bigger difference between the cases where beta is positive and beta is negative, because that's really where you would expect to see the difference between columns and platelets, right? Or rods and platelets, I suppose, right? But then again, because we haven't worked out the details in full, even in case beta is positive but 3D, I would prefer not to comment on the details because I would be just speculating. But I'm positive there would be some difference in there. I should think about it in more depth. Thank you. This is a great question. Thanks.
Thank you.
Okay. Any other question? If not, let's thank Giacomo again.